We dissociate orthogonal with perpendicular. Now, there's one notion that we haven't translated quite yet. Bhon's statistical interpretation. We can't just integrate over dx anymore, because dx doesn't exist. We're now in 3 dimensions. So how do we generalize 1D probability density integral all the way into 3D? For example, we now use these funky things to denote vectors, the bra and the ket. We've defined an inner product between 2 functions, not just vectors, which is just their integral over a certain interval. This generalizes to multiple dimensions, of course. We're going to define what we call normal functions. Now, a normal function will borrow from a normal vector, right? Now, at first you might think, hey, normal functions are weird, because wouldn't that require that the magnitude of f always be 1? Doesn't that only work for either constant functions or, step functions like this, sine of x, and not like the trigonometric function, like the step function, sine of x. But this is not what it means. What does normal actually mean? Well, a normal vector is a vector whose norm is 1. But what is the norm even defined as? Well, the norm is defined as the square root of the result of taking the inner product of the vector with itself. Hey, wait a second. What if we apply that to functions? So, if this is 1, then the integral over some interval of f squared, this has to be positive, at least if this is complex, then we can just take its modulus. That is that, then this is normal. Notice how striking of a resemblance this bears to the fact that this probability density function's integral over the entire real line is 1. Orthonormal to each other now. And just like orthonormal vectors make up a basis in R2 and R3, like I, J, and K are all basis vectors that are orthonormal, orthonormal functions can make up a totally cool basis of their own.